Okay, welcome back everyone. We're going to continue talking about Gauss's law today, and the hope is that you can start to appreciate how much easier it is to use Gauss's law than calculating it using brute force, calculating the electric field, that is. Okay, so in this example problem, we did this in the chapter 21 slides. I think it was probably the third or fourth video, where we found the electric field of a charge distribution. And we'll compare this to the answer that we found. And it turns out that that answer was fairly complicated. But what we're going to do right now is use Gauss's law to solve this pretty easily. And the first thing that we want to do is think about what the electric field is doing and construct an imaginary Gaussian surface that is going to work out. So if you were to look at this charged wire, if you looked sort of down the wire itself, it would look like a dot, and it would have a positive charge, and the field would be coming out radially from this. So this suggests to us that a cylinder would be a good Gaussian surface. Okay, so in this diagram in the upper right, we're looking at this sort of looking down the wire, okay, like if you held up your pencil and you look straight at it right at the point. But now in the diagram here on the page, this is a side view, so like if you were holding your pencil sideways. And what we're going to do is construct a Gaussian surface, and I'm going to be real careful to draw my Gaussian surfaces all the same color now. We're going to do sort of orange Gaussian surfaces. Okay, and it's going to be a cylinder, right? And it'll be at that point right there that we want. And so what we need to do is apply the definition of Gauss's law. And so what this tells us is that the integral of E dot dA is equal to Q enclosed over epsilon naught. We're always going to start with that. And our challenge is in different geometries to determine what E dot dA is and to also think about Q enclosed. So in this geometry, notice that wherever you are on the surface of this cylinder, that dA in purple is pointing outwards. So like we did earlier with the sphere, we can say two things. First of all, we can say that E dot dA turns into just E times dA. So in other words, E is parallel to dA. Okay? And we did this in a previous slide when we were talking about flux. Also, we can assume that E is going to be constant at the surface of this cylinder. So now we can write just simply E times the integral of dA is Q enclosed over epsilon naught. So to finish off the left side, we would say E times the surface integral of dA. Okay, now this is where you have to be careful, because what we want right here is we want the surface area that contains flux, okay, that has positive flux. Otherwise, it's not present. It's equal to 0, okay? So really what we could have done is we could have written that this integral is the two ends of our imaginary cylinder plus the wrapping, if you will. So the wrapping is as we go around, okay? And that area, well, let's just say that this cylinder has a length of L. And we don't know what that value is, but the surface area of this will be 2 pi y times L. Y is our radius, L is the length, and the circumference of the cylinder is 2 pi y. So if we unwrapped it, the surface area that has flux would be 2 pi y L. Because remember, the electric field is coming out this way. It's not coming out through the ends. And we'll talk more about that in a second. Now the right side, we need to find the charge that's enclosed. And we can use the fact that it has a linear charge distribution lambda, which is Q over L. Okay? So there's an amount Q and a length of L, which means that Q enclosed is just simply lambda L. We pop that in there over epsilon naught, and look at how easy this is. The L's cancel, and we get an electric field which is equal to lambda over 2 pi epsilon naught y. Now, if you remember from our previous calculation, remember we had to do crazy cosine and secant squared and all sorts of weird things, and we got a result earlier, if you think back, of E equals 2k lambda over y. Do you remember that? Well, remember that k is 1 over 4 pi epsilon naught. And so if you stick that back in there, you're going to get our answer right here. And so this is an amazing result. I did this in much less time than the other derivation. Okay, so that's an important thing to point out, and that's one example of how we use Gauss's law. One thing that you can do when you have time is you can look at the properties of these electric fields by going to this website. So we're going to go there, and I actually want to do the 3D electric fields applet, and you might want to click on that full screen version there. And so this is what we have. This is a point charge, and this is the velocity of particles. Let's change that to field vectors, and we can move this around for a spherical distribution. This would be a negative charge, right? And let's change that into an infinite line. Let's see if we have that. Whoops, that's a double line of charge. I clicked the wrong one. Let's try a charged line. Okay, now look at this. This is what we're talking about, that the field is radial. So if I look at it from the end, notice how all those are going in. We're going to reverse this so it's like a positive line of charge. See how those are coming out radially, and I can think about drawing a Gaussian surface that really is a cylinder. And now if I kind of rotate this, that takes a little bit of doing, and this is kind of like what we saw in our diagram, the field going away. Now the last thing that I want to point out about this is that you'll notice that these electric field lines are only going radially, that they're not going diagonal. And there's a very important reason for this. It's called the Ghostbusters rule. And if I go back a slide, okay, let's say that I had this charge creating a field going like so, and this charge creating a field going like so. Well, what would be the value of the electric field in the middle where they meet? We talked about this earlier in the unit, but there's only one value for the electric field at any point in space, and it would be the vector sum of those two fields. So it would only go up. Okay? And we'll talk more about this later on, but just recognize that the electric field is going to be going away from this line, and also we should say that E is perpendicular to the surface of a conductor. And that's for this reason, because all the charge on a conductor is going to go to the surface. So if I have a conductor that is a curved surface like this, all the charge will go to the surface and the field lines will just go radially away. Okay, so that's an important point. All right, let's do another practice problem. Okay, so we have a sphere of radius r with plus q in it, and we have a cube of side approximately 4r, and the question is, there's plus q, how does the electric flux compare for the two surfaces? Well, they're equal, because what does flux depend on? It's just Q enclosed over epsilon naught. Now you would need a computer program to numerically integrate this cube to prove it, but they're equal. Trust me on this one. Okay, so let's do another problem. This is to find the electric field of an infinite plane with surface charge density sigma. Now this is another problem that we did earlier, and it was in the context of a disk of charge that had R go to infinity. And we'll definitely come back to that to make sure that we're doing it right. Okay, so keep that in mind. So E as R goes to infinity. Okay, at a point right here. So if I have an infinite plane that sort of looks like that, okay, with a surface charge density of sigma, that is equal to the total charge over the total area, or a little bit of charge over a little bit of area. Okay? All right, so the first thing we need to do is to construct a Gaussian surface. And it's not entirely obvious, but the best Gaussian surface for an infinite plane is a cylinder. Now this is different from what we had before. Okay? Well, I'm going to try to draw. It's a dotted line. So this cylinder is going to intersect our surface in a circle. So this is where the charge that's enclosed by our surface is going to come from. Okay, now why are we picking a cylinder? Well, this is one of those things where people tried a bunch of different shapes, and it turns out that this is the easiest one mathematically. Okay, so we're going to set up Gauss's law. The integral of E dot dA is equal to Q enclosed over epsilon naught. So we want to think again, all right, what's the electric field doing for this infinite sheet? Well, if you think of it as having uniformly distributed positive charge, the field is just going to be going away from the sheet. There's going to be no components going diagonally because we're going to meet with another component going diagonally, and the vector sum will be just going away. Okay? So if the sheet is, for example, in the I hat and j hat directions, then all of the field will be in the positive and negative k hat direction. Okay? That's not super important, but we should recognize that E is going like this and like this. Okay? So, what about E dot dA? What happens with that? Well, dA is like this on the tops and the bottoms of the cylinder, and the side of the cylinder dA is going to be going radially. So that could get messy. However, E is going either up along the wall of the cylinder or it's going into, depending on your perspective. So, because there's a field line that's kind of going like this. So if dA is coming out, there's no flux through the sides of the cylinder. And that's super important. That means that the only flux is going to come from the top and the bottom. So when we evaluate the surface integral, we only need the surface area of the top and the bottom. Okay? Now, we don't know for a fact that the electric field is actually constant at the top of the cylinder, but let's assume it and let's see what happens. And we're going to find out that we get the same answer as when we did it brute force method. So we're going to pull E out of the integral and have the integral of dA. And E dot dA goes away. Remember, we said this before, that E is parallel to dA, so the dot product goes away. Okay, what about Q enclosed? Well, that's a little bit trickier, okay? It turns out that we can just write Q enclosed as Q enclosed is equal to sigma times A enclosed, okay? And let's say that A is the area of the intersection of the cylinder with the sheet, which means that the top has an area of A and the bottom has an area of A. And that means that if I do the surface integral of dA, I'm just going to get 2A. That is the area at the top and bottom of the cylinder. That's awesome because Q enclosed is just sigma A over epsilon naught. And now just look at how pretty this is. The A's cancel and the electric field is sigma over 2 epsilon naught. And that is exactly what we got previously with the disk that then turned into an infinite plane. And as a matter of fact, if you want to look at the exact expression for this, let me get back to my note here on this. Remember that the exact expression was something like 2 pi k sigma times 1 minus 1 over square root of x squared plus r squared. And remember that as r went to infinity, x, by the way, was the distance we were away from the disk, and r was the radius. Okay, so we said that that term went to 0 as r went to infinity, and so the electric field was just 2 pi k sigma. And this is another time where you can substitute that k is 1 over 4 pi epsilon naught, which turns into this expression that we found. So here's another example of where using Gauss's law made life so much easier and just allowed us to calculate an answer almost immediately. Now, it took time for me to explain what we were doing, but when you use it in practice, it goes a lot faster. Okay, so we're going to do a couple more examples in the next video, but I want to keep this one in a reasonable amount of time, so I'm going to stop here.